Okay, what I'm going to do is I'm going to go over simple stoichiometry first, and then we'll get into the more intermediate stoichiometry where we actually have more than one given. In this particular problem, we have one given. That's 567 grams of carbon dioxide. How many grams of water are we going to produce? So we're going from gaseous liters going to gaseous liters. Sometimes we're going to gaseous liters to grams, all these combinations. But the most straightforward one, the one I always start with, is grams to grams. Okay, now in your lab last week on stoichiometry, you did a calculation on the grams of sodium chloride. That was a theoretical yield. That's what we're calculating today. Theoretical yield. The actual yield is not the same thing. Actual yield is you actually weigh it. That's your actual yield. Then you're going to get a yield percent, which is actual over theoretical. Okay, so let's look at this problem here. All right, number one, balance the equation. Okay, so I went ahead and balanced it. So the coefficients are 1, 2, 2, 1. All right, number two is what's given. Now, this calculation is crucial to understanding when we have two givens. It's crucial. That's why I was telling you last week to make sure you go through and do some practice problems. Okay, so first step is, since we can't work with grams directly, we have to convert to moles. So first step is convert to moles. Now, carbon dioxide is 4401 grams per mole. So the grams have got to cancel. Okay, now we're in moles of carbon dioxide. Okay, and this was carbon dioxide. Now, the next step is getting moles of carbon dioxide to moles of water. That's a ratio from the balanced equation. So carbon dioxide coefficient is 1. Water is 2. And that's from the balanced equation. Notice carbon dioxide cancels. Okay, now we have moles of water. We need grams of water. So water is 1802 grams per mole. And we want the moles to cancel. And I've officially run out of room. So what we're generating is a theoretical yield. If everything went perfectly in this reaction, we would get what we're going to calculate in a second here. So theoretically, we're going to be able to get 4.64 grams of water. But what if we got 2.0 grams actual yield? To do this, so it's 2.0. We should have got 4.64, assuming our lab technique was perfect, which it never is, regardless of who's doing it. So to do a theoretical yield calculation, that is actual yield over theoretical yield times 100. So we have 2 over okay, 2 sig figs. So we have a 43% yield. Now, if you're a chemical engineer, this is one of your main jobs, is to maximize yield. Because if you're a company making a product, you want to maximize your profits, which means you want to get the most out of your reactions. And many chemical engineers design processes to maximize the yield. My first job out of graduate school was with Spreckels Sugar. And my job was to maximize the crystallization of the sugar. And also to modernize all the equipment. Because if you ever go into a sugar factory, what comes in is all muddy. Usually it's sugar beets. We're all muddy, and everything what goes out is just white crystals. It's amazing, the transformation in a sugar factory. So the first day on the job, I wore a suit. That was the last day and I ever wore a suit in that company. Everyone wore coveralls because it was a mess. One of the jobs I had was to find leaks. Anytime there's a leak, they call that the effluent is filled with sugar. That means they're losing product. So we had to find all the leaks. We had to redesign the crystallization process, but the process was to maximize the yield, actual over theoretical. And that's what chemical engineers do in various processes. For example, there's a chemist a long time ago, he got the Nobel Prize for this. His name is Haber, H-A-B-E-R. He invented how to take nitrogen out of the air and make ammonia. Because before that, they had to go to South America on these islands where there was tons of birds that crapped. And they would take the bird droppings on a ship and tow it back to the United States. That's all they did. Imagine being a captain of a ship where their cargo was bird crap. Okay, so up until Haber, That's what they had to do. And they use that for various things. Fertilizer for one. Anytime they needed fixated nitrogen, they used bird droppings. So Haber invented a way to take nitrogen gas and make ammonia. So no more crap shits, crap ships. Anyway, he got the Nobel Prize for it. Now, as a side note to that story, um, Einstein, he was German, and he was friends with Einstein. Now, this is when Einstein was still in Germany. And Einstein and him were, when World War I started, they offered both of them a job to make poisonous gas used in World War I. Einstein said, thanks, but no thanks, for moral reasons. Haber jumped on it. And Haber also invented mustard gas, which used in World War I. Now, the bottom line is Einstein came to the United States twice. Second time he was able to get in at Princeton. Haber died a very, very poor man. All this stuff with the military, he got arrested for being a war criminal and all this stuff. So high morals, A's. Okay, sorry about the stories. Okay, so yield. Actual over theoretical gives you percent yield. And that's what you're going to calculate on your lab. So the first calculation you do is theoretical yield of the sodium chloride. Then you weigh the sodium chloride after you dried it. That's your actual yield. So you're going to go actual over theoretical times 100. That's going to be your percent yield. Okay, so are there any questions about this guy? Okay, now this is the foundation for which we're going to build when we have more than one given. More than one given. Okay. We're burning ethane. Burning ethane. Okay. Ethane is C2H8. We're burning it in oxygen. Balance the equation. Okay. Equation is now balanced. Okay. Gives me grams of ethane, grams of oxygen. Two givens. And what are we supposed to do? How are we supposed to work this problem? Which given do we use? So that's step number one, is which given are we to use? The ethane or the oxygen given? Okay, so as a side note, if I have ten bicycle frames, 10 wheels, that's given. How many bicycles can I put together? Who said 5? Someone said 5. Okay. Why not 10? Because 10 frames, there's one frame per bicycle. That means with looking at frames, we should get 10 bikes. If we're looking at wheels, we can only get 5 bikes. Because it takes 2 wheels per bike. Okay, so in your head, it was Cindy that said 5, right? In your head, you did this calculation. First, we started with frames and determined how many bicycles are made. Then we started with wheels and determined how many bicycles we make with the wheels. The one that makes the least amount of bicycles is the limiting reactant. So in this case, The number of wheels limits the reaction, not the number of frames. But we had to do two calculations to determine that. And then how many frames were left over? 5. Okay, so we needed to figure out with 10 wheels, how many frames did you use? 5. What did we start with? 10. 10 minus 5 is 5. So the 10 wheels produced 5 bicycles, and we used 5 frames. That's the third calculation. How many of the non-limiting reagent did you use? Third calculation. The fourth calculation is we started with 10 and we used 5, so we have 5 frames in excess. So that's the fourth calculation. So you have so calculations 1 and 2 determines the limiting reagent between the two givens. Calculation 3 determines how much excess we have of the other given. Then calculation 4 determines how much is left over. Every single limiting reactant problem has 4 calculations, no exceptions. 4 calculations. And we're not talking about bicycles now, we're talking about chemistry. So, and these are going to be stoichiometry, stoichiometry, stoichiometry. 3 stoichiometric calculations. Okay, so let's do these. All right, so let's start with ethane. How much ethane is burned up when we get how much water out of this? Okay, so first thing is we need to calculate grams. So given to grams, or excuse me, to moles. Okay, and ethane is C2. That's 2402, two 1201s, 8 H's. So that's 808. So we're looking at 32.10 grams per mole. So grams have got to cancel. That means grams are on the bottom. Now, the balanced equation. Okay, so ethane needs to be in the bottom, water on top. Now we need to go from moles of water to grams of water. Okay, so now for the first calculation we have, let's create some room here. All right, so using the ethane to start with, we'd end up making 52 grams of water. Okay, if we started with the oxygen, this is the O2. Oxygen is 16 grams per mole. And there's two of them, so that's 32 grams. Okay, the ratio of oxygen to water in our balanced equation is 8 to 8. And then water again is 1802. Okay, so grams cancel, oxygen cancels, moles cancel, and what's left over is grams of water. So we have now 8 over 8 is what equal to? 1. So I don't have to worry about the eights because they equal 1. Now, if you'd like, you can certainly throw those in. Okay, so what is limiting the production of water? Oxygen or ethane? Oxygen because it creates less. Okay, so the oxygen is the limiting reactant. That means we're going to have excess ethane. How do we calculate how much ethane is actually used? Okay, we're going to start with our limiting reagent, which is the oxygen. So we start with 34.5 grams. And a lot of these numbers are reused again. Okay, so that gives us moles of oxygen. Now we're going to look at ethane and oxygen ratio. Okay, again from our balanced equation. So it's 2 to 8. 2 ethanes, 8 oxygens. And ethane is 32. Okay, now this calculation will tell us how much ethane is used if we totally use up the oxygen. So we use 8.65 grams of the ethane. We started with 34.5 though. So how much is left over? Okay, we go 34, start with, and we used 865. We had an excess of at 25.85 excess ethane. Now, as a chemical engineer, I would go, oh my God, that's horrible. We need to fix this. What do we need to add to make this number smaller? More oxygen or more ethane? More oxygen, yeah. We need a lot more oxygen to burn up that ethane. Exactly. So as a chemical engineer, that's what we do. We start adding more and more oxygen to the system and looking at the yield. Okay. The actual yield, now that's theoretical yield, is 19.4 grams. That's the theoretical yield. The actual is 567. So that's a 29.2% yield. Okay, so that's a limiting reactant problem in all of its glory. That's why I said last week, make sure you go through with one given, because it complicates things a lot when you have two givens. Okay. Do we have any questions about any of those calculations? Now, every one of these is going to have 4 calculations, no exceptions. First two is required to figure out which limits the reaction. The third one is what's the excess. Fourth one is, excuse me, the third one is not excess. The third one is to calculate how much you used. The fourth one is excess. Every single problem has 4 parts. Now, there could be a 5th part on the yield. This depends on the problem. Now, this problem here, we're starting with liters of ethane. Ethane is a gas. And we're starting with molecules of water. 2 givens. Same basic deal. 4 problems. 4 problems. Now, I said last week you're going to have a take-home problem for test 4. Okay, it's going to be a limiting reactant problem. Okay, because these are kind of stressful with a time limit. It's an understatement. So I want you to do it at home. And obviously you can have full notes. Okay, so let's do another one. So no questions on these guys? Yeah. Wait a minute. Yeah, how did I get 34 point? Yes, you're right. I should have used, since ethane is the excess, I should have used the excess. So you're absolutely right. Thank you. So I should have used 23.2. Now the percent yield is not going to change because none of that is okay. So what's going to change is the excess. And again, thank you for pointing that out. You're absolutely right. So what you use plus excess is going to be what you started with. Very good. Very good catch on that. Okay, I'm going to go over one more problem, and then we're going to jump off to lab. Okay, so we're working with burning ethane again. Now, ethane is a very common gas in natural gas. Natural gas you get out of the wall is a combination of methane and ethane. Methane is a one carbon alkane. Ethane is a two carbon, and they usually mix. They both burn equally well. They're also very cheap, especially if you live in Texas. Texas produces by far the most natural gas state in the country. It's also almost it's the third biggest state in the union as well. So, and they stink. A good friend of mine, there's a lot of natural gas in the valley here as well. And my friend, his company cleaned the filters because when the natural gas comes out of the ground, it's very dirty. There's a lot of junk and a lot of sulfur stuff. So what his company made filters that filtered the natural gas, and it turned into a very profitable company. That was his job. So there's a fair number of natural gas wells in the valley here, probably more, and in also along the coast in Southern California as well. So California makes a lot of natural gas as well, but Texas by far makes the most. Okay, so let's see here. Okay, we're starting with liters of ethane and grams of oxygen are consumed. So again, we need 4 calculations here. All right, so since ethane is a gas, we're going to be using 22.4 liters, and we're going to assume this is all at standard temperature pressure, which it isn't, but that's what we're going to assume. Okay, so we have to start with 23.2 liters. Now, if you take 2B, Chem 2B, or Chem 12A, I believe it's 12A or 20A, I forgot which one it is. That's the STEM organic OChem. You'll learn a lot about things like ethane and methane and combustion products. I mean, out the yin yang. But all you need to know now is ethane burns nicely in oxygen. Okay, so our convert to moles. Then we need to go from ethane to water. So ethane is 2, water is 8. So our ethanes cancel, our liters cancel. Now we need to go to water. We want to know molecules of water. That's Avogadro's number. Okay. So looking at 23. Okay, so I'll give us, if we're starting with ethane, we're going to end up yielding 249 times 10 to the 24th molecules of water. Okay. Or 34 grams of oxygen. So we convert to moles. Then we need to go from oxygen to water. The balanced equation. So oxygen is 8, water is 8. We have the 8 over 8 again is 1. Okay, so moles cancel, oxygens cancel, grams cancel. By the way, okay, let's grind this out, see what we get. Okay, so what's the limiting reactant in this problem? Ethane or oxygen? Huh? Oxygen, 23 versus 24. Okay, so oxygen is a limiting reagent. So if we totally burn up O2, how much of that ethane is burned? So for the third calculation, we're starting with the limiting reagent. getting it to moles. So oxygen is going to be 8, and the ethane is 2. Okay, so we have 1.62 times 10 to the 23rd excess molecules. So it's basically the same thing again. We're just not using grams to grams. Okay, so those are really two good examples. And if you go to, are there any questions about that? Hopefully I didn't make any mistakes with the math. The third part? Okay, so first two steps determine what limits the product. Okay, then you take what's limiting, that's what you start with for the third part. So in our case, it was the oxygen that's limited, right? And then we want to know how much of the other stuff we used up. So that's the second part of that equation. So step 3 determines how much is actually used of the other stuff, the non-limiting stuff. Let's go back to the first problem with grams, because I think, okay, so first two steps determined that oxygen limits the reactant, right? 19 versus 52. So the third step is to determine how much of the other stuff, in this case, it's the ethane, did we use up? Okay, we used up 8.65 grams of it. But we started with 23. So that's where the fourth calculation is we subtracted how much we used from what we started with. Okay, so let me, okay, so steps 1 and 2 determines which limits the reaction. Third step, now, the limiting reactant, all of it's used up. So there is none left. It's totally consumed. So if it's totally consumed, we have excess, and how much is that? Okay, so we need to determine how much of the other stuff is needed to burn the limiting reagent's oxygen. That's what the third calculation is for. Then this one here determines the actual excess. Is this better? Destiny, is this better? Okay. All right. So those are two good examples, particularly this one here. Now, I've got lots of videos on doing limiting reactants besides this one we're doing today. Number two, I have a lot of worksheets for you for practice. Are there any more questions on this? If we go to Files, Unit 4, this is where all the practice worksheets are located. And towards the bottom, you will see all these limiting reagent problem worksheets with answers. Okay?
After, by the time I actually got the hold lifted, I was blocked out of like, I'm in a chemistry class, but like I emailed you and it does not, I don't basically, unless the professor would work for me, but I'm looking at.
Okay. Let me end this video or the recording.